Hi, in this video we are going to discuss on what are the various types of feeds which can be used in the parabolic reflectors. Okay, so first of all, let us see what are the various features or what are the various parameters which would influence the performance of the antenna which has a reflecting surface. Okay, so first one is the dimension of the reflecting surface. So we usually prefer smaller dimensions than a huge dish antenna. Suppose we have dish antennas at home or some reflecting antennas for commercial applications. We would always prefer antennas which are not so huge, right? So dimensions of the reflector is one of the performance parameter. Next is spillover. So what is spillover? So when the feed which is placed at the focus of the paraboloid reflects, gives the primary pattern, okay, and hits the secondary reflector, that is the bigger one, the paraboloid, the illumination which comes out is usually parallel to the axis of the parabola, right? Now, there are some part of this illumination which is coming out of the feed which doesn't hit the reflecting surface and it misses the reflector. So this is called as spillover. So spillover is that part of the feed antenna radiation which misses the reflector, that is the parabolic reflecting surface. Next is aperture blockage. So when the feed is placed at the focus of the parabola, because of the dimensions of the feed, some of the radiation does not come out of the antenna and they are blocked by the feed. Okay, so this is called as aperture blockage or the feed blockage. Usually this blockage is because of the feed location. Okay, next is illumination taper. So towards the edges of the reflector, the illumination which is coming out of the feed would reach. But then these radiation which are reaching the edges of the reflecting surface get tapered. Okay, so this is called as illumination tapering. So this is at the edges of the reflector, which is actually reduced when compared to the maximum radiation which is towards the center of the reflecting surface. Next is reflector surface deviation, or it is also known as defocusing. Okay, so what is defocusing? Defocusing is when the antenna is displaced from the actual focal point. So usually the feed and the antenna, there would be a proper alignment. So when this is not happening, that is called as defocusing. Next is cross polarization. What is cross polarization? Sometimes the polarization which comes out of the reflecting surface is supposed to have a definite or specified polarization. So when the polarization which comes out of the reflecting surface is orthogonal to the actual polarization or desired polarization, it is called as cross polarization. Sometimes it is written as XPOL, X polarization. Okay. So this is because of the polarization which is orthogonal to the desired polarization. So sometimes the radiation which is coming out of the reflecting surface get cross polarized. So it becomes orthogonal to what is actually desired. Okay, so this is cross polarization, which is not a desirable parameter. So we have to check for these points. Next is feed losses, which occur because of the connections between the feed and the receiver section. So there will be waveguides and transmission lines which are connected from the feed and the support of the feed. So there will be losses because of these transmission lines. Next is antenna feed mismatch. So there would be impedance mismatch at the feed because of due to some of the energy being reflected back by the antenna surface, and then these energy being re-entering the getting inside the feed and the transmission lines which are connected to the feed. So this brings impedance mismatch between the antenna and the feed. Okay, this is also not desirable, so we have to check for this. Next is non-uniform phase and amplitude distributions. So we don't need a parabolic reflector which has a feed at the source at the focus point with a radiation pattern that has phase variations, right? We don't need these phase variations and amplitude variations. So that is the desired quality. desired quality is that the antenna should not have any phase or amplitude variations. Okay, so this non-uniformity in these variations should be taken care of. Okay, yeah, so these were the qualities. So an ideal feed for a paraboloid reflector is supposed to be at the focus with a radiation pattern that has no phase variation, and the feed should be in such a way that it produces the desired aperture illumination at the reflecting surface, and the directivity also should be sufficient enough that allows all of the field radiation to be intercepted by the aperture without any spillover, right? So these are the ideal feed, but then these ideal qualities are not usually fully accomplished. Now the radiation pattern which is produced by the feed which is placed at this focus is called as primary pattern, and the radiation which is occurring from this surface, that is the paraboloid, is called as the secondary pattern. Okay, so this is one figure which I got from Google for a paraboloid with a front feed, that is the feed is placed in front of the reflecting surface exactly at the focus. Okay, so this is an antenna, reflector antenna with a front feed. Okay, so the only problem is there is aperture blockage because of this feed. So when the reflector, when the illumination from this feed hits the surface and then comes back here, there is aperture blockage because in this part you will not get the radiation. And you can see there are some supports for this feed. So this support will also contribute to the aperture blockage. Okay, advantages, the manufacturing cost is less. Okay, and then we get satellite reception, microwave, point-to-point link, etc. And then the geometry is simple. Okay, so this is one way that we can place the feed at the focus of the parabolic reflector antenna. So there are other examples for the placement of these feeds in parabolic reflector. Let us see. So this is the figure in your textbook. Okay, so let us see one by one. So the first figure you see here is a simple half-wave dipole here with a parasitic reflector. So this directs most of its energy towards the antenna aperture, and this can be used as a feed for the paraboloid. Now, why do we place this parasitic reflector? We know that the dipole would give a radiation pattern in this direction and as well as in this direction. But you don't want the antenna to radiate in this direction. You want the illumination to be exactly pointing to the reflecting surface. So we keep a parasitic reflector here. Okay, so dipole is of limited utility as a reflector feed since it is difficult to shape the primary pattern. Primary pattern is the pattern which is coming out of this feed. And then it is limited in power handling, usually at higher microwave frequencies. So dipole is not much preferred in such cases. Instead, we can use an open-ended waveguide, which is preferred over a dipole for higher frequencies, microwave frequencies. So there could be a circular waveguide also or a rectangular waveguide also. Usually we'll prefer a circular, for this circular paraboloid, we might prefer a circular open-ended waveguide. So circular waveguides usually operate in dominant mode TE11, right? So you can also use rectangular waveguide operating in dominant mode TE10, right? But if you keep a rectangular waveguide here, it will not result in a perfect symmetrical secondary pattern, right? So when compared to rectangular waveguide, circular waveguide would be preferred as a feed point at the focus of this reflecting surface. Okay. So rectangular waveguide is not preferred because the dimensions in E and H planes are different, correct? But still, circular waveguide is preferred over dipole antenna. Now that figure is not shown here. Okay. Now, so above all those, when we need more directivity, okay, when we need more directivity from this feed point, we prefer open-ended waveguide horn, like which is seen here. Okay, so this horn can be made to provide asymmetrical feed illumination, that is fan beam, right? We saw fan beam in the previous video. Fan beam is asymmetrical feed pattern when you need azimuth beam width to be narrow and elevation beam width to be broader than the azimuth. we use asymmetrical illumination. So that illumination is called as fan beam. So when you need such things, we can use horn antenna as the feed for the parabol. Okay. So these two which you see here, A and B, are rear feeds. So this is rear feed using half wave dipole, and this is rear feed using the horn antenna. So you can see this horn antenna has a support. So this contributes to aperture blockage. So as a rule of thumb, we have a performance constraint here. So that is that the intensity of the radiation from this feed, which is coming towards the edges of this reflector, that should be usually 10 dB below the maximum radiation which is coming out of this part of the reflector surface. Okay, so this aperture illumination at the edges, okay, should be 10 dB below that, the maximum, below when compared to the maximum radiation coming out of these parts. So it was found that with primary feed pattern, which is 10 dB below towards the edges, the first side lobe in the secondary pattern is in the vicinity of 22 to 25 decibels. Okay, so if you increase this primary pattern illumination at the edges, the side lobes are going to increase. So it is better to have a primary feed pattern which is 10 dB at the edges. Okay, 10 dB down the maximum value. Okay. Now another parameter which should be discussed is F by D ratio. Okay, so 1 second. Yeah, F by D ratio. F by D. So what is F? So for this, for a reflector antenna, F is the focal length, and this is the aperture dimension. That is this one. Okay, so this is the aperture dimension. So most practical reflector antennas have F by D ratio in the range of 0.3 to 0.5. So what does this ratio mean? So suppose we have a smaller F by D ratio. Okay, so small F by D ratio means we are going to have a deep reflector. Okay, small F by D, that means this is going to be small, right? Focal length is going to be smaller. So we have a deep reflector, which is difficult to illuminate, right? And what is meant by large F by D ratio? Large F by D ratio means we are going to have a shallow reflector, right? The shallow reflector is easier to support and to position mechanically. Okay, so but the feed must be placed very far from the reflector in this case, correct? Because what is higher F by D ratio means higher F. So the focal point is very large, so you should place the feed very far away from the reflector. So that's the only constraint. The farther the feed is from the reflector, narrow will be your primary pattern. What is primary pattern? The pattern which is coming out of the feed, right? So that is the primary pattern. So in large F by D ratios, you have the reflector surface would be very shallow and the feed point, right? So very shallow reflecting surface means you have to place the feed at a very large, because F is going to be large, right? So, and then as the feed is going to be very far from the reflecting surface, your illumination is going to reduce. So it is not going to reach the entire reflecting surface. Okay. Yeah, so the primary pattern should be narrow in this case so that spillover is less. Okay, but the feed should be larger. That means the feed should be larger. Understood? So, yeah, that are the features for large F by D ratio. Usually in tracking radars, we prefer large F by D. Okay, yeah, so that is about F by D ratio. Next is the feed supports which can be. So you can see various supports which are seen in this figure. So usually in this dipole and the waveguide horn which you see here, A and B, these are open-ended. This is open-ended waveguide, right? So these can be arranged to feed the parabola from the rear. So these are the rear feed, right? You can see here rear. So there are other types of feed systems which can be used, like how you can see in the C. Okay, 1 second. Yeah, so this one. So in this is what is called as front feed. Okay, front feed, and here we use a horn radiator. So that is also placed at the focus itself. Okay, but then you can see this is all the support for this horn antenna which is used here. Okay, and this contributes to very high aperture blockage, right? This support obstructs the entire aperture, the radiation which is coming at this. So this radiation is not going to reach it, right? So this is going to block the radiations. So these obstructions which are due to this feed and its support, this reduces what? This reduces the antenna gain, that is G. And this also increases the side lobes. And because of this, some of the radiated energy becomes cross polarized. So cross polarized sometimes is written as X, like this, cross polarized. So this aperture causes what all? It reduces the gain, right? It increases the side lobes. It causes the radiation to be cross polarized. Okay, so this brings you the adverse effects of aperture blockage. So there could also be something else called as impedance mismatch at the feed, and that is because of some of this radiation re-entering the feed. So it could go like this, and then it could hit back the feed itself, and this is the mismatch. So there occurs the mismatch between the antenna and the feed. So both aperture blockage and this mismatch due to reflection can be eliminated by not employing this design. So it can be eliminated by something called as offset fed reflector. So you can see in this diagram. So this is a parabolic reflector with an offset feed. So what happens is the feed is placed at the focus. You can see that this is the focus of this parabola. But then you can see that the feed in this arrangement is placed at the focus, but it is this is horn antenna. Okay, so this horn antenna is tipped upwards, so it is squinted, it is offset, right? It is not along the axis, right? It is offset. So it is offset with respect to the parabola axis. So this is the axis of the parabola. So with respect to the axis of the parabola, this is offset. So lower half of the parabolic surface is removed actually. Only the upper part. So the part which is seen in this figure is actually contributing to the reflections, right? So this field which is outside the path of the energy which is reflecting from the antenna surface, hence there is no aperture blockage. There is no problems in the radiation pattern because of the blockage of the aperture, right? So hence there will not be any impedance mismatch also, okay, which is given by the speed. Okay, so this is one way to reduce the aperture blockage and the impedance mismatch which was occurring because of this front feed using horn to this design. Okay. Now, so even though this offset feed eliminates the aperture blockage and the mismatch, it introduces some other issues. So we know what is F by D ratio, right? So it is focal length divided by the diameter or the dimensions of the reflector antenna. So usually this F by D ratio is greater than that of the conventional paraboloids which you see. Okay, so for this offset reflector, this F by D ratio is usually larger. Okay, so that is one issue. Other issue is usually it is very difficult to support such a feed, such an offset feed. To support mechanically, it is very difficult. So that is another issue. And because the asymmetry is increased in this case. Okay. So because of this increased asymmetry of this particular design or the geometry, when illuminated by a conventional linearly polarized feed, cross polarized radiation lobes are produced. So when you feed the linearly polarized waves, certain cross polarized lobes are also produced. So this, what will this do? It will reduce the radar system performance by indicating false targets. Okay, so this the problem here is cross polarization. So though the aperture blockage is reduced and the impedance mismatch issues are reduced, there is cross polarization issue still, and then the difficulty of supporting such a feed mechanically. Okay, so these are the issues. So how to reduce this cross-polarized side lobes? So these cross-polarized side lobes of this single reflector offset fed antenna can be reduced by having a dual reflector antenna. Okay, so we will see what is dual reflector antenna. Now, these are the real time. So this is one offset feed reflector. So you can see the feed is offset here. Okay, so the lower half doesn't contribute to any radiation. So hence this blockage is not going to interfere with the radiation pattern. So only the upper half is used. Hence you don't have any issues. The reflections can properly happen. Understood? Now this is a dual reflector offset. Okay, so you have the feed which is placed here. You can see this is the feed. See, this feed is here, and then you have a other lens which is ellipsoid which is placed here, and then you have a reflection. So this is dual reflector. Okay, offset. So this figure is not there in your textbook. So this is for your knowledge that I've put this figure. Okay, so this is dual reflector offset. So which reduces the cross polarization effects. So that's all about the various types of feeds which are used in parabolic reflector antenna. Next topic is Cassegrain antenna. So let us see about Cassegrain antenna in the next video. Thank you.